Today we continue our discussions on the belt drives. This is lecture number 31. Now, in the last class we started with the belt drives. So, just to recapitulate very quickly, we started with the belt material. Now, normally for the belt drives, leather, rubber, plastic and fabric are the materials which are most commonly used for the manufacturing of the belts. Now, in the leather belt material, you are having, you can see the oak tanned and the chrome tanned type of leathers are available. In the rubber, basically what happens, a canvas or cotton duck impregnated with rubber. This is the construction of the rubber belts. Plastic belts, as it was told, it consists of a thin plastic sheet with a rubber layer and which could be having more number of plies. What is the number of plies means? The number of layers of such plastic belts. If we put it in one after the other, then we call this as the ply. And last one we consider as the canvas or the woven cotton ducks. So, these are called the fabric belts, which are normally used for very temporary and short period belt operations. So, this was the place where we stopped in the last class. So, if we continue, the first thing is that typical belt drive specifications. What we understand by typical belt drive specifications? Now, normally what happens that whenever you are designing a belt, then the most important part is the material. The decision of the material you are using for a belt depends of course onto the service. So, depending upon the different services, different types of materials are being used. Then you can see the point number of ply. So, what is the number of ply? As I told you, what is the total number of plies that with which the belt is made of. So, that the cross sectional thickness will depend upon the number of ply you are using in a belt. Maximum belt stress per unit width. So, what this means? This means that the belt is always in tension, as you know. So, what is the capability of belt to withstand a tensile stress is what is the maximum belt stress per unit width. Why per unit width? Because from the earlier 3 points, one has already taken a decision roughly that we should use for this particular purpose this type of thickness, although the final thickness will come into picture later on. But somehow or other it is, as because all design procedures are little iterative in nature, one has to think of at the initial a starting point. So, only thing that depending upon the total tensile strength which will be calculated depending upon the design situation, depending on that particular tensile strength, one has to select for the thickness, because the stress, if you know, multiply by area gives you the total tension. So, out of that, if we fix the thickness at the beginning, then width becomes a variable. So, normally it is recommended that the belt stresses are being given as per width. But this situation also may change. Sometimes what happens, you know, that instead of such specification per width, one also can find out in design data book the stresses coming onto the belt are just given in terms of pa, means Newton per millimeter square. So, as I told you in the design, it will be normally given as MPa, that means it will be Newton per millimeter square. So, if you directly get the stress value, then if you just multiply it by the cross sectional area, then you get the total stress. So, in both the ways a belt strength is specified. So, next comes that the density of the belt material and coefficient of friction for a given belt material. Now, once again just I will give a discussion at different speeds and for a specified speed. Okay. What this means? This particular situation means that depending upon the belt speed, the tensile strengths also vary. So, what happens that the chart normally provided for design gives you the strengths at varied speeds, or it can give the strength at a given speed, and you have to incorporate what are the factors. You have to incorporate the actual strength through a factor. So, that is the reason at different speeds and for a specified speed are the two terminologies normally used. So, now I suppose that you understand that this could be the chart for the stresses either for this situation at different speeds. So, you do not have to do any corrections or incorporate any corrections. For a specified speed means you have to incorporate a correction. Density of the belt material is very much required, and in this particular case I would like to say the density of the belt material are normally provided per unit length per unit cross section. That means, for a given cross section for an 1 meter of belt length in SI units, what is the weight of the belt material? That way the density of the belt material is normally specified. The density of the belt material specification is required because you have to compute in the basic equation the centrifugal force arising due to the rotation of the total belt. Coefficient of friction, as you know, will be again required in the basic equation, and this coefficient of friction obviously depends on two situations. One is a belt material, another is a pulley material. Say pulley material is cast iron and the belt material is leather. So, there will be a coefficient of friction stated for leather and cast iron, and similar the situations will be varying whenever materials of the pulley or the belt will change. Next, we come down to the same ideas what I have just discussed, the modification of belt tension. When maximum belt stress per unit width is given for a specific or specified speed, then what happens in that case? You require to go for a correction factor, which is we have defined as C speed to modify the belt tension, and when it is operating at other than the specified one. So, just which one I just told you is being given over here in written. Another important factor is that what we call is the angle of wrap is less than 180. See, normally for a belt, if we look to the situation, that is, this is a pulley, and if we are having a belt like this, this is your 180, this alpha value, you know, this from here to here, this is we called as an alpha angle of wrap. So, this is normally all the design values given in the design handbook are based on 180 degree. However, this 180 degree will be maintained when both the driven and the driving pulleys are the same in diameter. However, if one is larger than the other, then obviously you have seen in the earlier figures what we discussed, that the angle of wrap onto the smaller one or the smaller pulley will be less than 180. So, if it is less than 180, then you understand that the contact area between the belt and the pulley decreases, thereby the power transmission capacity will be changing, will be decreasing accordingly, depend from what we get at 180 degree angle of wrap. So, thereby what happens that a reduction in the belt strength is to be considered. Now, a very rough guideline, although you might be getting the exact values for this reduction, but normally as in thumb rule one can think of that the belt stress to be reduced by 3% for each lesser angle of wrap or specified in handbook as by factor CW. I think this is what it was covering for each, for each 10 degree. Okay. That means, if it is 3% less for each 10 degree. So, if it is 170 degree, then how much you get? You reduce the strength by 3%. If it is 160 degree, then you reduce the strength by 6%, and so on and so forth. You can get this particular angle of wrap factor, which we are considering over here as CW. So, what we have learned in these two slides, that the specifications how it is given in a design data book. That means, one has to know the material, one has to know the belt stress per unit width, or what I told you, that in certain cases the things becomes very simple, that directly considering all these aspects of 1 degree wrap angle or different speeds, a gross value of the belt stress may be considered. Say for example, a gross value of belt stress for a leather material can be taken as 2 MPa, 2 megapascals, means I just write down. So, that is something like 2 MPa. So, this is something an average type of situations you can take. So, same thing if you are considering for leather belt, then the value will be coming out to be something around 1.5 or so. Okay. So, these are also well utilized in design to consider the belt stress. So, other situations requirement for belt drive design is the the belt density and the belt and the pulley, between the belt and the pulley what is the coefficient of friction. Now, selection of flat belt, how we consider the selection of flat belt will be discussed in this particular slide. Now, normally what happens that belt drive transmission ratio or the transmission ratio of the flat belt drives is normally limited to around 1:5. Next thing is that, although it is there, I instead of this point number 2, I go down to the point number 3. The center distance is dependent on available space. Well, this is true that center distance is dependent on available space. So, you have to compromise over the space availability, but one important thing you should remember, normally for the flat belt drive practically there is not much of a limitations of the center distance. However, that does not say that you put an infinite center distances. Okay. Normally it depends relatively on the experience, but somehow or other in a situation like that, that center distance something around twice the sum of the 2 pulley diameters is all right. Okay. It could be little higher, normally it should not be lower than that, and that factor 2 can also vary. Well, all these statements suggest that I am not giving you a definite value. The reason is that the first statement what I made you, really there is no limit for the center distance, but you know, if you are having a very large belt, then the belt flattering and due to the weight of the belt, the centrifugal forces. So, that those are certain aspects that unnecessarily one should not go up for a very large center distances. Again, at the same time, if you are making the center distances too small, then what is happening, the flexing of the belts will take place very rapidly, thereby some amount of belt life will be lost. So, some compromise depending on the experience, space availability now is a guideline for selecting the center distance. But you should remember that normally for a starting point, the dl plus ds into 2, that means twice the sum of two pulley diameters, little over that is quite good. But the situation will change of course for other type of belt drive, we will come down to those points. Now, the choice of belt material depends on type of service, that I have already told. Belt specifications are obtained from handbook. So, what you get from the handbook I have already dealt up in the earlier slide. So, depending upon the different kinds of handbooks, all handbooks will not give you in the similar manner, there will be some changes. However, what I mean to say, those basic parameters are more or less specified in all the handbooks of design, and from which you will get the initial guideline as far as the belt stresses are concerned. Because our primary design objective is what? The primary design objective, although we will be seeing after some time, still I am just telling you, is the belt should not fail in operation. Okay, so that thereby the stress value is very important, and other situations like belt length, which is also very important. One of the vital factors I think I have told you in the last class is this flat belt are not endless, means it has to be joined. So, a proper care should be taken while joining these two belts at their interfaces. Well, coming down to the second point in the slide, what you see that depending on driving shaft speed, driven shaft speed pulley diameters are to be calculated and selected from available standard sizes. This means that all the pulley drives what you are going to design have a specific idea, means what is happening, that what is the prime mover. Suppose it is the electrical machines. So, electrical machines will be operating at a certain speed, say standard 3-phase induction motor speed will be around 1440 rpm, 1450 rpm, like that. So, that will be your this driving pulley shaft speed. However, the other one, the driven one, will be the actual one which will be running a machine element, something say a pump or a machinery it will be running, not necessarily a machinery it will run, say a pump or some grinding, floor grinding, means you find in standard shops, okay, or a rock crusher, whatever may be. So, it has got another speed. So, what happens, that you have to design the pulley diameters accordingly, so that the speed of the driving and the driven shaft are as per your requirement. Now, that will be can be conveniently found out from the relations of the speed ratio or the velocity ratios, etc. Now, here I would like to say that normally all the pulley, the belt drives will have a certain amount of slip present in this case. What is the amount of slip? We have seen that amount of slip will be roughly around 3%. However, if the value of slip is not given, which is normally the fact that in all designs you do not know the slip a priori. Okay, in that particular case what happens, that as because the slip amount is not going to change your pulley dimension to that extent, people may ignore the slip at the beginning. Well, why this statement I am making? Because you can see that after you calculate a dimension, then what happens, that that dimension, calculated dimension as a matter of fact may not be as per the standard size. Okay. So, it will be always economical that you choose the pulley from the standard size or the stock of standard sizes available in the market, otherwise economically it will not be viable. I mean, it will be more costly if you try to manufacture each and every time the pulleys as per your need. So, once you find out the standard sizes, you will be always finding out the exact speed ratio that what you wanted to conform to may be differing slightly. Well, so that is the thing, that slight difference in the speed ratios or the velocity ratios could take care of your slip situations. Okay. If it is given, fine, but otherwise you can just simply ignore the slip. The reason is that it is not a very great amount. So, and it will be taken care of during this adjustments of the dimensions and other things. Okay. So, the coming down to this particular idea, once again I read it, that depending on driving shaft speed, driven shaft speed, pulley diameters are to be calculated and selected from available standard sizes. This point is clear to you. Now, I come down to the fourth point, that the belt speed should be within 15 to 24 meters per second. This is from that experience and that some calculations, that it has been found out that for a flat belt drive, good speed is something which should be lying between 15 to 25 meters per second, say 20 meters per second. Okay. We just taken some average value. So, that what is the idea, that you consider designing means the computing the diameters of the pulley, taking a velocity in your mind, say 20 meters per second. Then you calculate the pulley diameters and then adjust the pulley diameters to the standard sizes, again recalculate what is the new belt speed, because this belt speed is an important parameter which will be useful for what you understand, useful for finding out the belt stresses, as I noted pointed you earlier, and depending upon the belt speeds, as a matter of fact the stresses in the belts will be changing. Now, last 2 points are already clear to you. The choice of belt material depends on type of service and belt specifications are obtained from handbook. Now, we come down to this particular concept of selection of flat belt. Now, first of all, you are going to design the belt drives depending upon a design power. What is that one? You ought to transmit certain amount of power through the belt drive, that is your objective. Now, what happens, that depending upon the service conditions, what are the service conditions? Means machinery may run for only 2 hours a day, a machinery can run only for 24 hours a day, a machinery can run in a very clean environment, a machinery can run in a very rough environment. So, depending upon all these situations, what happens, the effect comes onto the belt stress and thereby the belt life. So, certain service factors are always given in the design handbooks. Roughly it is classified as a light shock, medium light duty, medium duty and then heavy duty, and one could be like that a continuous operation, one could be a shock operation like that. So, under these categories you will be finding out that different types of service factors are recommended. Now, from the given handbook you can find out that what could be the appropriate service factor for your use. As a matter of fact, the space and the time do not permit here to reproduce all the service factors that are listed in the design handbook. However, a rough guideline could be something like that. You just see it is given in blue color, that is, it is the service factor is normally 1.1 to 1.8 for light to heavy shock loads. Well, this is an guideline. Okay. So, if you want to be very conservative, you can just straight away take 1.8, but that will be actually it will not be very economic for you in that particular case, because conservative designs are always too costly. Okay. So, design power P design is given as service factor multiplied by required power. Required power means the power which you intend to transmit. Now, from basic equations, design power is given as P design equals to B into T into etc., what it is given over here. Now, I think for this expression I will give you a brief idea, so that you can understand the genesis of this equation. This equation is simply from two fundamental equations what we have derived in the last class. Well, what we can see is that you know what will be the power? Power P will be given as T1 minus T2 into V. What is V? V is the bell speed and T1 and T2 are the bell tensions. So, unit Newton into meter per second. So, Newton meter per second. So, this is effectively is the watt or power. So, once you get this T1 minus T2 into V is the power. So, here what we have used, this power is actually your design power, okay, that you understand by multiplying by service factor. Now, out of this, if we can replace T1 by some means, then our problem is solved. You know very well T1 minus m v square by T2 minus m v square equals to e to the power mu alpha. What is this one? Mu is the coefficient of friction, as you know, and alpha is the angle of ramp. Okay. Now, which alpha you should take, for the larger pulley or for the smaller pulley? Now, you understand, if the pulley material and the belt material, of course, the same belt is running, if the pulley materials are the same, then what will happen, that the product of mu into alpha will be lower for which one? For the smaller pulley. So, normally for all situations, smaller pulley is the guiding pulley. That means, all the designs are based on the smaller pulley, because the power transmission capacity on the smaller pulley will be smaller than what you will be obtaining if you have considered the larger pulley. So, you understand that the guiding feature will be e to the power mu alpha for the smaller pulley, and the value of mu alpha should be expressed in radians, that you should be keeping in your mind. Well, so from this equation you can get the value of t. Okay. Now, what is happening? I think I have mentioned about this m. See, this m is basically what? It is the weight of the belt material per unit length per unit cross section. So, if we look into this particular equation, then what is V square? The V square we know it will be coming out to be meter square per second square. So, we multiply it by kg per meter cube and we multiply into meter square. What is meter square? The meter square stands as B into T. What is B into T? The width into thickness. So, meter square gets you this this particular meter cube and this cancels. Okay. So, you are having kg meter per second square, or this is equivalent to your unit Newton. So, once you substitute this particular one in this value, so this is very important just to look into the what you call the unit point, unit part. So, once you are satisfied with the unit, this is coming out with the same unit. So, we will be putting these values accordingly. So, what we will be putting? We will be putting Bt and kg per multiplied by rho. Okay, this is the expression for this one. So, once you are substituting T2, then entire expression comes out to be what? T1 minus a function of T1 and other parameters. So, you can, and sorry, I put this bracket and multiplied by V. So, once you get this one, you take this T1 common. So, what is coming out to be T1 multiplied by all these things, which is coming over here. Now, this T1 is basically is what? The maximum belt stress. Now, this maximum belt stress is an allowable stress in the belt multiplied by its cross sectional area, isn't it? So, we replace T1 by this particular value and allowable stress into B into T. How you take the allowable stress? Either a simple way, either you take something around 2 or 1.5 or 1.6 as I told you, or you can consider this particular sigma A from the design data book per unit per unit length and unit cross section, these values will be given. Anyway, you are in a position to know this particular value. So, if we come down this particular expression, if we put it in the proper manner, well, I have given you this ideas, then what we get? We get okay, we get this equation P design equals to B T, that you can see B T we have taken it out. So, in this case, if when you have taken this B T taken you have out, then this sigma dash P rho V square into this V. Now, you can see once again we have used this sigma dash. This sigma dash parameter, as I told you, is actually specified value modified by a speed factor and modified by the angle of wrap factor. In certain cases, you require this equation, or you can get a value directly. So, if you get this one, then obviously is much more better that no other corrections are required for that matter. So, this is the design equation. So, what you get from this design equation? You see, you know this value from the design data book, you know this value from the design data book. This is your choice of the speed. What should be the choice of your speed? Say roughly 20 meters per second. and this thing you are getting 1 from the material property and alpha, this alpha from the geometrical property. So, all these things are known to you. So, what is unknown? You do not know the value of B t. So, once you can set this particular value of B t from this equation, then what you get? You get the cross sectional area. Now, once the cross sectional area if you have obtained, then a choice of what should be the typical width and thickness could be different combinations, and you see that from the standard availability in the market what should be the width and what should be the thickness. A compromise between it should not be very thin and very wide, because the more you make the wide, then what will be happening, the pulley has to be, the pulley materials will be more, because you have to make a larger pulley width. Okay. Similarly, too large of a thickness in that direction might be keeping your per unit cross sectional length and weight of the belt. So, a compromise between these two can be very easily made from your experience and the availability. Okay. So, from where you can set these two values. So, this gives you a very good way of designing or the selection. So, this is a mixture of how you do the design, means as a matter of fact, and the selection. So, here design part is not very much, it is a selection basically. Okay. So, once you find out the typical cross section of the belts, etc., that is all right. I think one part I just wanted to tell you that in this particular expression, while you are deriving the value of alpha, you have already chosen the center distance, isn't it? So, once you have chosen the center distance, and which is fixed, the pulley diameters already you have calculated. Now, it will be very easy for you to calculate what should be the total length of the belt, because in the very first lecture already you have seen the formula for the total belt length requirement is given over there. So, in this particular case, what is happening, that we have assumed the belt drive to be an open one, isn't it, because we have taken a smaller pulley diameter and a large pulley diameter like that. Had it been a cross belt drive, then of course, those beta parameters or alpha parameters would have been the same. Basically, we require the alpha parameter. Anyway, that is not preventing you or that do not make any change in the design procedure. Whichever the type of belt drive you choose, it is both suitable for either a cross belt drive or a open belt drive. Now, this is the idea by which you consider the design of the design and selection of the flat belts. So, this is the next slide, which again is a repetition of what I have already told you. That means, what we understand is this one, that already we have computed the area of belt cross section, that is already over. Okay. I have just told you. Belt width, thickness and number of ply is obtained from belt specification table. So, that is where one should iterate, okay, that which could be a best combination to suit a situation. Now, the last one, what requires little bit of this discussion, which we have not done yet, is that calculated belt length, which is normally kept 1% short for correct initial tension. Now, in this particular case, what is happening, that you know the role of initial tension in power transmission, that we have already discussed. So, you can go on increasing the initial tension till a limit. What happens, that T1 could be maximum and T2 may be coming out to be 0. However, that is not done in that manner, but anyway this is a possibility also. That means one has to introduce a good amount of initial tension. Again, just to repeat, that initial tension will dictate that what should be the bearing loads onto the shaft, and thereby the bearing designs and other things are also dependent on this particular initial tension. Now, normally what should be the optimum initial tension? Instead of calculating in actual practice what is being done, the exactly belt length you have taken up and calculated and selected, then what you do, from your calculated value of the belt length, make the belt length roughly, it is a just and guideline that you make it 1% short. All right. Now, this 1% short is not always true, it depends depending upon number of plies also. Well, what I am giving you are just an indicative value, and if you make it 1% short and then make it the joint where you should take care, once again I am telling you the joint should be very carefully taken care of, otherwise noise will come and belt might snap without giving you any notice. Then coming back to the thing what I was just telling, that this 1% shorter belt length will automatically create an initial tension, which for all practical purposes has been found to be quite optimum in nature. So, this is the idea. You design, everything is over, cut a belt length, but while cutting you take some amount small. What is that small amount small? Roughly around 1% length you take smaller and just join it and put it onto the drive. So, that solves your problem. So, this is the idea by which one can go for the selection of the valve frame. Now, you know that another very important and widely used belt drive is a V belt drive. Now, we will going to discuss about some aspects of the V belt drive. Now, you can see this slide on the V belt drive. Here you please look to this figure. This is actually what is shown here. A V belt drive means, the look is something like an V had we completed the entire situation. Okay. Now, this is the wedge angle. Okay. And of course, you understand the pulley should be something like this to conform the V belt. Here I think I give you an idea that the pulley, the belt should not go entirely inside the pulley, but it will be something like this. This is a best way of designing. Some portions will be like this. Okay. So, within the pulley the particular V belt is situated. Now, here the nomenclature of the V belt stands like this. As it is given, it is thickness, this is the top width, and you do have a neutral axis. What is a neutral axis? That means when you are bending the belt, where the bending of the belt will take place, because the bending of the belt will take place whenever it is just passing over a pulley. So, in that case a zone will come which we are defining here as a neutral axis, where there will be no stress, and other sides, one side it will be compressive stress and other side it will be tensile stress. Now, this particular distance what we call as a pitch line, this is the pitch line, okay. So, which is passing through the neutral axis as pitch line, and and this obviously will be the inside line. So, that means, if you are having an belt drive through which a V belt, I am just giving an exaggerated view, all right, V belt is going. So, we have something like this as a pitch line, and this one is an inside line. Okay. So, this is an inside line and this is the pitch line. So, these two parameters are very important because of the fact that while calculating or while using the equations of belt drive, then whatever the diameters or the I mean to say the pulley diameter or the belt length L, all what we compute are based on this pitch line, means what is the values you are getting or using are all pitch line values. So, if you want to come down to the inside line, then appropriately you have to do some subtractions, some value subtractions to come down to the inside line. Okay. So, this is the cross section of a pulley, I am sorry, V belt cross section as it is given in this figure. And next what we will see that normally these are the V belt specifications. What are the V belt specifications we understand? Now, here I would like to say one thing, that these particular cross sections are normally available in the terms of A, B, C, D and a little higher side also E, that I have not included over here. So, let us consider as the situation to be A, B, C and D. Of course, we do have something like E section also. Now, A section means of course a thinner cross section, I mean a smaller cross section, that you can understand. 13 is the width and 8 is the thickness in millimeter, and D on the other hand you can see 32 is the width and 19 is the thickness. So, obviously given the material of the belts being same, the D section has got a larger power transmission capacity. This D section has a larger power transmission capacity compared to an A section belt. So, that is the reason you can see the kilowatt range. So, if you are going to transmit anything within 5, you go for A section. If you are going to transmit something within this C zone, say 10 or 15 or 20, then you go for the C section. Now, if you are going to transmit something around this particular value, you can see although you can go for 2 over here, but sometimes the 2 means it is going towards this side of the A section belt. So, normally people can go, means this is an overlapping zone, either you can choose A or you can choose B. So, some amount of overlapping zones will be always there. However, one should concentrate in this way, that somewhere in the mid zone or like that is a better way, because you can see for a given power transmission of very large, can we not do with an belt A? Of course, you can do with the belt A. Suppose you require, just an example, you require 2 sections of D belt, two numbers of D belt, D section belt, then what will be the number of A section belts? It will be 2, it may be 10, it may be 12 or something like that. Without calculation it is very difficult to say, but something around this way, looking at the horsepower, I mean kilowatt capacity range, one can understand that if you are using an A section belts, then you have to use more number of belts compared to a D or C belt cross sections. Okay. In this case, what will happen? The situation is that you require a pulley with more number of grooves, thereby the pulley becomes heavy and it becomes costly, it actually creating a more load onto the self weight of the pulley itself will cause a more load onto the shafts. Okay. So, thereby the choice of the belt section, whether it should be A, B, C or D, depends on the situation of power transmissions. However, a brief guideline is as given in this particular slide. So, once again if we look into this one, then you find that in the belt specification some other things are also mentioned, that is a minimum pulley diameter is 75 mm, 125, 200 and 355. Means what is happening basically, you know, that when it is passing over a pulley, it has to bend a lot, isn't it? Now, these V belts these V belts having a different thicknesses. So, if it is going for a very small pulley, this 90 mm thickness, then the belts are to be bent in a very great extent. Okay. So, thereby it will cause a huge amount of stress in these areas. Okay. The bending stresses will be more. So, obviously depending upon the situation, one has to look for what? One has to look for that what should be this minimum pulley diameter. This pulley becomes a guiding factor, as because A section belt has got a lesser thickness, its minimum pulley diameter is 75, and in the same logic the D can be going to as high as 350 mm pulley diameter. So, in this particular case, one is warned of the situation that use of minimum pulley diameter is always recommended while going for V belt drive designs. Okay. So, in this one or the belt specifications table, I think everything is quite clear. That means, you know that what are the type of belt sections A, B, C and D, how it is designated depending upon the power transmission capacity, and we do have a belt section E also, but it is not being specified over here because those are for the very high capacity. And another important factor is that looking at the flexing of the belt, this word is used very much. Flexing means how much you are bending. Okay. So, how much the flexural strength is getting changing, means that is a flexural strength you have learned earlier, that means it is plus minus plus minus. Okay. So, these repeated stress situations also are taken care of, okay, while considering the belt design in terms of certain factors that we will be looking very shortly. So, this is another important thing, that means how you designate a V belt. That means the belt or the V belt, we always talked about the pitch line, this is pitch line and this is inside line. Okay. So, obviously this belts when we are considering, so it will have a pitch line length and it will have a inside length, which is shorter. Obviously, the inside length is shorter. Now, while just drawing this figure, one important thing came into my mind is that these V belts do not have any joints. These are continuous belts, and what is happening that these particular belts are manufactured without joints. So, that means what is happening, that certain standard lengths of the belts are only available. You cannot have the belts of length of your choice. You have to just select whichever the belt is very close to your situation. So, while designating a belt, the interesting fact is that it is never designated with respect to pitch length, but it is designated with respect to nominal inside length. Suppose after calculation you have selected a B section belt depending upon the power transmission, and you computed that the belt length is 1016 mm. Then or something else, and in the catalog you find that 1016 mm is the closest to your calculated length. Then you have to choose this 1016 mm belt and you have to designate this B1016/40. This is in millimeter. In the same data book you will be finding out the another value is given in inch also. So, this is the designation of a V belt, B1016/40. Now, what we find out, the relationship between inside length plus x will give you the pitch length. So, what is that one? That if you have, as just refer to this figure. So, this inside length plus some length will give you pitch length. So, this x, what is the value of x in millimeter? If it is A section 36, B section 43, C section 56 and D section 79. Well, with this designation of V belt, I think we stop here for today. We will continue our lecture in the next class. Thank you. Good day. We continue our discussion on the belt drives. So, today's lecture is lecture number 32, and you see, just a quick recapitulation what we have done in the last class. So, this is for the V belt drive, and you know that the V belt specifications are as given over here. So, there are 4 type of sections mainly. Also I told you that there is also an E section present. So, depending upon the kilowatt range, one has to select the typical belt for the use. Next one that we just talked about, that the designation of V belt, how we consider this. So, what happens that if we have a belt length something like this, then we know that this is the inside length and this is the pitch length. So, by the formula etc. what we have learnt earlier, we can determine the pitch length, where by use of this chart we have to find out that inside length, and this inside length whatever has been computed should be chosen as a nearest that is available.